Hello. In this video, we'll be talking about systems of equations that are consistent and inconsistent and that have independent and dependent equations. I will show you some example problems that will give a broader understanding of the systems that are consistent and inconsistent that have independent or dependent equations. So let's look at a problem. Let's look at a particular problem. Let's say that we have x plus y is equal to 4, and also x minus y is equal to 2. Now, to check to see if the system is consistent, basically, you want to see if it has at least one solution. And if it has one solution, then you know that the system is consistent. If the system has no solution, then it's inconsistent. Now, we can also determine if the equations are dependent or independent. Well, if this system has infinitely many solutions, or if it has just at least one uh, solution, that will determine if it's independent. But in this case, if you have a system has infinitely many solutions, then the equations will be dependent. And you can determine this by solving the system using various techniques or solving this system graphically to show that. Now, if the system has one solution or no solution, then you can see that the equations will be independent. And graphically, it will show that that it will have lines that may be parallel or lines that will actually intersect, which in fact will show independence. Now, when we solve the system, as I said before, there's several different techniques. There's the elimination method, which is considered the addition method as well. And then you have another technique for solving the system called the substitution method. Now there's other ways in solving this system to find a solution by using the Gauss-Jordan elimination or the Gaussian elimination. You also have this technique called the Cramer's method, but we'll get more involved with those techniques later on in later videos. For now, just let's look at the substitution method and solving the system to get a solution. Okay, so if we actually take one of these equations and solve for either one of the variables, we will substitute that equation with the isolated variable into the other equation. So let me show you. So we have x plus y, say we take x plus y is equal to 4 and we solve for y. So we're going to take negative x to both sides. So then y is going to equal to negative x plus 4. Now we'll take this equation and we'll substitute it into the other equation. So this will be now x minus, now watch, negative x plus 4, which will be equal to 2. We see that. So as we do that, how will we simplify this? We will say x, and then we're going to distribute the negative signs here to this term and to that term. So this will be x plus x minus 4 is equal to 2. So now watch. This now will be 2x minus 4 is equal to 2. So in this case now we want to solve for x. And when we solve for x, we'll just simply, what we get for x, we'll use back substitution and plug that or substitute that value into the other equation. So we're going to add 4 to both sides here. I'm getting very low, I'm getting below the screen here. And this will be equal to 6. Let me move to the top of the screen up here and start again. Well, continue. This will be 2x is equal to 6, right? When we divide 2 to both sides, x is going to equal to 3. Now, we have 3 for our value of x. X is equal to 3. Now we're going to use back substitution, right? To substitute this value into either one of the original equations and then substitute, and then solve for y. So this we'll use and say x plus, whoops, we don't want to do that. We want to plug in, we want to solve for y. So let's go back here. And now we will say 3 plus y is equal to 4, right? Now we'll solve for y. And so y is going to equal to 1. So in this case, this system has at least one solution. And we have for x is 3 and for y is 1. Right? So this system is in fact consistent. It's consistent. And what does it say about independence? Well, if a solution or if a system has at least one solution or no solution, in this case it has one solution, the equations are independent. So we can say the equations are independent. Okay, so that's how we solve this numerically using the substitution method. This is the substitution method. So let me put that on. This is the substitution method. Now, I would like to now show you, now we know that this equation or this system is consistent and the equations are independent. Now, we know if we solve the system using another technique, we're going to get the same answer, the same solution. However, I just want to share with you another technique in finding the solution to the system. So we're going to talk about now the addition method. The addition method. So let me clear this. Okay. Let's use the same problem. X plus y is equal to 4. And this will be x minus y is equal to 2. Now we'll call this the addition slash elimination method. Okay, so in the elimination method, basically what we're trying to find, or in this case, the convenience of this problem is that you have your coefficients by the term which are the same but opposite of one another. So you can eliminate x or you can eliminate y. You can manipulate these, but sometimes you don't have to manipulate any of the numbers or the coefficients because it may be already set up for you. For example, if I want to eliminate y, that'll be very easy because you have this is understood to be 1y here, positive 1y, and negative 1y. So in this case, since its coefficients are the same but opposite of one another, we can easily eliminate y. So when we actually use the elimination method slash addition method, then all we have to do is add the two equations together for the first step. So we have x plus y is equal to 4, and this would be x minus y is equal to 2. So in this case, what do we get? We get 2x is equal to 6. You see this? So now we solve for x. And once we solve for x, we can use this thing called back substitution. X is equal to 3 again, right? So we can plug this in or substitute this into the original, any one of the original equations. And when we do that, we say that 3 plus y is equal to 4. And then we take negative 3 here and negative 3 there. And so y is equal to 1. Here we have our solution, which is the ordered pair 3 and 1 again. This actually means that when you graph these two equations, the intersections is going to be at the point of 3 and 1. So this is the addition method on how to solve the system, right? And we see that this is going to be also still what? The equations or the system is consistent and the equations are independent. Okay. Now, as we look at this, there's another technique now to and I'm gonna show you this one. This one is basically alluding to both techniques, the substitution and the elimination methods. However, I'm going to show you something with these two equations. Let's clear this. Clear this. We use the same problem. Let's use the same problem again. And mind you, these systems they get more complex and more difficult. But we'll later we'll go into solving more complex systems. I just want to show you the basics first before we get into that. You can actually now from your algebra, you remember um, these equations, what type of form these equations are in. This is considered standard forms. Both of these equations are in standard form. And then you have this thing called slope-intercept form. But we're going to change both of these to slope-intercept form. And I'm going to show you something. When we change these to slope-intercept form, we have y is equal to negative x plus 4, right? And then, of course, if we take let's just do this step by step, right? So to solve for y. So we know how to change this in the slope intercept form, and for you folks out there that kind of missed and maybe just starting to watch this video, let me just show you how I got that. If we have x plus y is equal to 4, I want to change this to slope intercept form. So, and that's to solve for y, isolate the variable y. We're going to get y is equal to negative x plus 4, or y is equal to 4 minus x, either one. So that is one. Now let's do this one. X minus y is equal to 2, right? So we again solving for x. So this will be negative y is equal to negative x plus 2. Now again, we're trying to solve for y, right? We're not negative y, but we want to solve for y. And when we do that, we want to divide what to both sides? We want to divide negative 1 here and negative 1 there. So this will be y is equal to x minus 2. We see that. So now we got the two new equations that are in slope intercept form. So we can actually take these two, and this is, these are basics. You can actually take these two equations, right? And you can set them equal to each other. And you have this thing called variables on both sides. So if we have negative x plus 4 is equal to um, x minus 2. We want to get all the variables to one side, right? I like to use the coefficient variable with the coefficient or the term that is smaller to do the work to both sides. So in this case, I want to say positive positive x here, and of course positive x there. It's always good habit to use the to move the variables first and not the numbers, not the constants. So this will be 4 is equal to 2x minus 2. Everybody see that? So what are we going to do now? We're going to solve for x. And when we solve for x, we're going to add 2 to both sides. And look at what we get. 6 is equal to what? 2x. Everybody see that? Take a second. I'm going to have to move the screen so we can continue with this problem. Okay. So continuing with this problem. Okay. So we had what we had? We had 6 is equal to 2x, or 2x is equal to 6. So when we divide 2 to both sides, x is going to equal to 3. So again, we're going to use back substitution again. We use back substitution to plug or to substitute the value of x into the original, one of the original equations, either one, it doesn't matter. And again, well, to solve for y, that is. And then we have 3 and 1. Again, see? So again, the system, because it has at least one solution, is consistent, and it's also what? It's also independent. The equations are independent.